So I'm going to walk you through the calculations for the kinetics lab. So what I did was I just pulled out some sample data. So when I ran through the reactions, this is what I got for my times for trial one and trial for all these different mixtures for 2 trials. And I'm going to switch over to Excel because I think this first part is done. It's so much easier to do in Excel. I'll show you exactly what to do. What you're going to find the average time, and then you're going to have to convert drops to milliliters here and here, and then find the total volume. So all I did was copy this chart and I put it into Excel. See, same times and everything. So to find the average time, that's the first thing we have to do. All you really have to do is add these 2 times and divide by 2. That's what we're averaging. So 55 plus 53 divided by 2. And in Excel, you would just do equals and then parentheses, click on this guy, add, click on this guy, divided by 2, boom, 54. You can do that in your head. If you don't want to use Excel to do that, that's fine. You can do that by hand as well. So for Excel, I would just have to highlight that cell and then click over on the right till that cross sign comes and drag down, and it's going to do all those calculations for me. So you can confirm that this is 175, this is 64, 89 plus 91 is going to be 90. So those are your average times. We're going to need those, especially when we get down here, because we're going to have to find the relative rate. So the next part is to convert drops to milliliters. So remember, we weren't measuring out milliliters in this lab. We were measuring by drops because it was such a small volume. So the drop to mill conversion, let me just write that down for you. There are 20 drops is 1 milliliter. So 20 drops equals 1 milliliter. So in the first step, I have 10 drops, and there are 20 drops in 1 milliliter. So that's going to give me 0.5 mils. So basically all I have to do is take the number of drops and divide it by 20, and that's how I'll convert to milliliters. So if I do that in Excel, it's nice and easy. I can just say equals, click on that cell, divide it by 20. Do the same thing all the way down if you don't want to drag equals this, divided by 20. I'm going to just drag it down just to make it quicker. So those are my my volumes in milliliters. So it's not really a lot of milliliters. Same thing over here. So water equals this divided by 20. It should be 0, right? 0 divided by anything is going to give you 0. Drag that down. And then my milliliters over here do the same thing. 2 divided by 20. Great, I got 0.1 and then down. So if you just look at these volumes for a second, we're adding water really just to keep the total volume constant. We want the total volume to be the same. That's going to make it a little bit easier when we do our when we find our molar concentrations down here. But if you see what we did here, we changed. We have 10, 8, 6, 8, 4. So we changed this volume a lot. This one we pretty much kept it at 2 the whole time. We only changed it once here. So the whole goal of this experiment really is to see, we're trying to find the rate law, and the rate law really depends on the orders of the reaction. So we want to find the orders of the reaction. And so, we'll get there. So first, just filling out this chart, we're eventually going to have to find molarity, but we want to find the total volume. So to find the total volume, you're just going to add up this volume plus this and plus this guy, and you get 0.6, which makes sense, right? 0.5 plus 0 plus 0.1. 0.4, 0.1, 0.1, that should also be 0.6. 0.3, 0.2, 0.1, that should be 0.6. 0.4, 0.2, that's 0.6. So we kept a constant volume of 0.6 all the way down. Okay, so this first chart, not too bad. Find the average time for both trials. Also, make sure that your trials agree that, I think within 10 seconds, they should be pretty close. I got pretty good results there. Okay, so we found the average time, and then we converted the drops to milliliters. Now, when we get to the second chart here, we're going to look for the relative rate. So I just copied these average times down here, just so I can refer back to them a little bit closer. And then the relative rate is just going to be 1 divided by that time. That's it. So relative rate was 1 divided by time. Let me just write that down so that we know, right? We said relative rate, which is 1 divided by time, and that's in the lab. So that's how we're going to find our relative rate. So we're going to say equals 1 divided by this time. Boom. Okay. And I'm going to drag that down. Boom. And this one's a little weird. 1 divided by time. Only weird because I have this thing here that's not letting me drag copy my equation down. Now, to find the concentration, so we found all these things. Now to find concentration, we are going to use M1V1 equals M2V2. Okay, so all the information we need is up here in this table, but it's kind of like hidden. So up here, we initially started with a 0.1 molar sodium thiosulfate concentration. So we had 0.1 molar of this guy, and then we changed the volumes. We kept the total volume the same, so M2 was always going to be the same, V2 was always going to be the same, and we're calculating M2. So we can't just say this is the concentration all the way throughout the reaction because we're mixing it with something else. And that we're increasing the volume, the total volume is going to change, so this concentration is going to change. So I have 0.1, that's my first molar concentration. My first volume is 0.5, and then my second volume, my total volume, is 0.2, and I'm going to calculate the new molarity just for this concentration. So let me write that down. We will do it in Excel, but let me write it down over here. So again, we're using this equation, M1V1 equals M2V2, and we're going to have to do this for both reactants. So we said the first reactant, this guy, like the sodium Na2S2O3, right? That first concentration was 0.1. That's right on the bottle. That's the one that's on the bottle. That's our stock solution. And the first volume that we used was 0.5 milliliters. And we're going to do this in milliliters. That's okay. M2 is what we're looking for. So basically, we're looking for this concentration after it's been mixed. So it's the new concentration after it's been added to the volume, something with a greater volume. Sorry, the total volume is going to be bigger. So I have 0.6 milliliters. Great, so when we do this, we're going to do this 5 times for the sodium thiosulfate. We're going to do it 5 times for the hydrochloric acid. The hydrochloric acid has a different starting concentration. But for all of this, for that first column there, this stays the same, this stays the same. This is what's changing. That 0.5 mils is what's changing. Right, let me just switch back to Excel really quick. So you can see we have 0.5, then that volume changes to 0.4, 0.3, 0.4, 0.2. So that's the part that's changing. So I'm working on this column here, and I'm using M1V1 equals M2V2. So what do I get there? I'm going to divide both sides by 0.6, divide by 0.6. So I'm going to have 0.1 times 0.5 divided by 0.6, right? So that's M1, this is V1, this is V2, and I'm solving for M2. And when I work that out, I should get 0.0833, something like that. Let's see if we get the same thing in Excel. So in Excel, I'm going to have equals, my initial concentration was 0.1. That's what it tells me over here. That's my initial concentration. And my initial volume for that particular trial, for trial 1, was 0.5. And my total volume was 0.6. And I'm just going to type in 0.6. You could reference this if you want to. 0.6 is going to be the same all the way down, so I'm not going to worry about it. So great, I got 0.83 there. We're going to do the same thing for everything in here, right? So the only thing that's going to change now is instead of having 0.5, I have 0.4. So I'm going to have 0.1 times 0.4 divided by 0.6. And then the next one I'm going to have 0.1 times 0.3 divided by 0.6, and so on and so forth. So I'm going to just drag that down. And then over here, let's retype this one. All right, so I have 0.1 times, where am I, 0.2 divided by 0.6. Okay, good. And that makes sense, right? So if I look at these concentrations, look at these volumes, I cut this volume in half, and that cut the concentration in half. That makes sense. So I know I got those right. I can also check my work because I know this is 0.4, this is 0.4. I end up with the same concentration, which is important when we're going to choose which reactions to compare in order to figure out what the orders of the reactions are. So for the HCl, we're representing it by H plus because HCl, when you put it in water, it's going to associate into ions. It's the H plus that's reacting in this reaction. The chloride ion is just a spectator ion. Same thing with the sodium, right? We didn't consider the sodium over here. That's just going to be a spectator ion. The real reaction's happening with the H plus and the S2O3. So H plus is 1 molar. See, this guy was 0.1. This initial concentration is 1. So I'm going to use M1V1 equals M2V2 again, but now my M1 is 1 all the time. My initial volume is 0.1. My final volume is still 0.6. So let's work that out on this page here just to set this up. So for HCl, I'm also going to use M1V1 equals M2V2. I have 1 molar, that's my initial concentration, and my initial volume was 0.1 milliliters. M2 is what I'm looking for, and my total volume was 0.6. So I'm just going to divide that by 0.6. I know I didn't put my units in here, just so you see where we're going. Milliliter divided by 0.6 milliliters. So that ends up being 0.167. 0.167 molar, and that's the first H plus concentration. So that is, after I mix these two reactions together. So this is 1 times my H concentration divided by the total, let me just type that in there. Doesn't really matter. 0.6. Good. So 0.167. So I would do the rest of them the same way. 1 molar times 0.1. Again, we only changed it in this one trial, right? Trial mixture 4 is the only one that's different. So everybody else should be the same. I'll still type this out because why not? 1 times 0.1 divided by 0.6. And I should get exactly what I got over there. Good. Thank goodness. All right, so now the fun part. Now is the fun part. Now we can start working on the orders of the reactions. I have an equation in there, so it's already done for us, but I'm going to show you how we got that. So just like we do in class all the time, we're going to pick 2 reactions to compare. So how do you know which reactions to compare? You're always picking one where you're picking them where one concentration is changing and the other one's staying the same. Okay. So which one here is changing, which one's staying the same? So if you look at 2 and 4, the S2O3 concentration is staying the same, and this guy's changing. So we're definitely going to want to compare 2 and 4. And then in 1 and 3, this one's staying the same, and this one's changing. So let's just use all the data. You could compare 1 and 2. I'm going to do 1 and 3, and I'm going to do 2 and 4. So we'll do 1 and 3 first. So what I'm really looking at, okay, so here and here, I'm going to write my rate law, and then I'm going to look at which rate is bigger and put that rate on top because I don't want to get a fraction. So let's just refer back to, like, what is the rate law? What does that mean when I say rate law? I have rate is equal to, sorry, oh boy, okay, rate is equal to K times S2O3 2 minus raised to some power m. We're going to try to find that power. And then H plus raised to the n. So the rate is equal to K times reactant, each one raised to some power. And that m and n, those are called the orders of the reaction. K is the rate constant. We're going to solve for that after we solve for m and n. And then the rate is what we already calculated as, 1 over time. So we know the rate. So in the table, what do we have? We have rate data and we have these concentration data. We want to solve for M, N, and K. So the first thing we're going to do is we're going to pick 2 reactions, like we said. We're going to do rate 1 and 3 first, rate 1 and 3. And let's see, where's rate 1 and 3? So I've got 1 and 3 down here. So rate 1, the relative rate 1 is 0.019 and 3 is 0.011. So if I do 1 over 3, that's a bigger number, so I'm not going to get a fraction, which is great. It doesn't really matter. You'll get the same answer if you do it the other way. I just like to not get fractions when I'm doing those. And then let's see. So these are my other concentrations that I need. Great. And so one side should kind of drop out. So I'm going to do rate 1 over rate 3. So I'm going to set it up first. I'm going to say rate 1 over rate 3, and it's going to equal rate over rate, which is equal to K times concentration raised to the M times concentration raised to the N over K times some concentration raised to the M, concentration raised to the N. So I look at these values again on the table. Rate 1 was 0.019 and rate 3 was 0.011. Rate 1, 0.019, 0.011. And from the table, this concentration is 0.083 and 0.167, and this guy down here is 0.050 and 0.167. Okay, so again, just pulling out 1 and 3, so 0.05, 0.167, 0.83, 0.167. All right, so how does that help us? What kind of things cancel here? So 0.019 divided by 0.011, that's going to give me 1.7. This gives me 1.7. Oops, 1.7. My k's are going to cancel. 0.67 to the end, 0.167 to the end, 0.167. Those just cancel. And then I end up with 0.083 divided by 0.05, which is 1.66. And then I'm going to raise all of that to the nth power. Okay, so if you look at that, 1.7 equals, this is, if I round that up to 1.7, 1.7 equals 1.7 raised to the m, I can eyeball that and say that that's going to be 1. If your numbers end up not being that close, you can take the natural log of both sides. So then I would do, right? So if I took the natural log of both sides, natural log of this, natural log of this, when I do the natural log of this, my m comes out in front. If you're not familiar with log rules, and you might not have seen that before, don't worry about it. So we have m. This is what happens when you take the natural log of something with an exponent. That exponent comes out in front of the natural log. M times natural log of 1.66 is equal to the natural log of 1.7. So natural log of 1.7, when I put that in my calculator, I get 0.53 equals m times, this ends up being 0.5068. I'm going to divide them both by 0.5068 to solve for m. 0.5068, so I end up with m is equal to 1.05, which is about equal to 1. Okay, so I have m equals 1. I'm just going to go to the closest whole number. They don't have to be whole numbers. Usually when we do them in class, they're whole numbers. Now, the next part that we want to do, that's great. We solved for m. Now we want to solve for n. So the way we're going to solve for n is we're going to pick two other experiments where one concentration is changing and the other one is not. So we already did 1 and 3. Let's look at 2 and 4. So 2 and 4, the S2O3 is staying constant, but the H plus concentration is changing. So we're going to compare those two. If you look at the rates, sorry, over here, the rates, 0.016, 0.016, the rates are the same. So that part's not going to help me. But if I do 4 over 2, this 0.33 is bigger than 0.169. So I'm going to do that one. So I'm going to do rate 4 over rate 3 in this case. So I have rate 4 over rate 3. Right. Ooh, that's not what I wanted. All right, so we'll do rate 4. I'm sorry, rate 4 over rate 2. I don't know if I said 3. Rate 4 over rate 2. I have my rates equals K times concentration raised to the M, concentration raised to the N, K times concentration raised to the M, concentration raised to the N. So rate 4, 0.016. Rate 2, 0.016. They're both the same. Okay, K. This one is 0.067, and this one is 0.333. This guy is 0.067, and this one is 0.167. All right, so these cancel, I end up with 1. My k's cancel, these cancel, and I end up with 0.33 divided by 0.167, which gives me 2 raised to the n power. And so anything raised to the n power, anything raised to the 0th power is going to give you 1. The only way that I can get 1 here is if n is equal to 0. So try that out in your calculator. 2 raised to the 0th power will give you 1. So my rate law ends up looking like this. Rate is equal to K times S2 O3 2 minus raised to the m power. We found that m is 1, and then times H plus raised to the 0th power, because n is 0. If we want to simplify that a little bit, clean it up, this is not going to matter because anything raised to the 0th power is going to be 1. So your final rate law looks like rate is equal to k times S2O3 2 minus raised to the 1st power. So that's the rate law. That's what we were looking for in this step. And now that we have the rate law, we can solve for the k. I'm going to make a